Hey, what's up, my Treadwell Eagles? Hope you're doing well. Today we're going to be discussing an article posted by the CDC, which is the Center for Disease Control, and they're kind of the main people right now who are fighting against the coronavirus. And so they have this article out that explains vaccines really well. And so we're gonna read this article, and hopefully this will give you an idea of what a vaccine is and potentially what scientists are trying to do when they're developing a vaccine for coronavirus. Um, so let's read this article, and I hope you learn a lot from it. Make sure at the end you click the link below in the description. There's a quiz that I want you to take that just has some reflection questions on this article. So let's get started. So understanding how vaccines work. Vaccines prevent diseases that can be dangerous or even deadly. Vaccines greatly reduce the risk of infection by working with the body's natural defenses to safely develop immunity to disease. This fact sheet explains how the body fights infection and how diseases work to protect people by producing immunity. The immune system, the body's defense against infection. To understand how vaccines work, it helps to first look at how the body fights illness. When germs, such as bacteria or viruses like the coronavirus, invade the body, they attack and multiply. This invasion, called an infection, is what causes illness. The immune system uses several tools to fight infection. Blood cells contain red blood cells for carrying oxygen to tissues and organs, and white or immune cells to fight infection. These white cells consist primarily of three things: macrophages, B lymphocytes, and T lymphocytes. Macrophages are white blood cells that swallow up and digest germs, plus dead or dying cells. The macrophages leave behind parts of the invading germs called antigens. The body identifies antigens as dangerous and stimulates antibodies to attack them. B lymphocytes are defensive white blood cells. They produce antibodies that attack the antigens left behind by the macrophages. T lymphocytes are another type of defensive white blood cell. They attack cells in the body that have already been infected. The first time the body encounters a germ, it can take several days to make and use the germ-fighting tools needed to get over the infection. After the infection, the immune system remembers what it learned about how to protect the body against disease. The body keeps a few T lymphocytes called memory cells that go into action quickly if the body encounters the same germ again. When familiar antigens are detected, B lymphocytes produce antibodies to attack them. So those memory cells are kind of the key to immunity here. They're the ones that make sure if those germs come back again, they can attack it quickly. And so you're not experiencing the symptoms for that disease. How vaccines work. Vaccines help develop immunity by imitating the infection. This type of infection, however, almost never causes illness, but does cause the immune system to produce T lymphocytes and antibodies. Sometimes after getting a vaccine, the imitation infection can cause minor symptoms such as fever. Such minor symptoms are normal and should be expected as the body builds immunity. Once the imitation infection goes away, the body is left with a supply of memory T lymphocytes as well as B lymphocytes that will remember how to fight the disease in the future. However, it typically takes a few weeks for the body to produce T lymphocytes and B lymphocytes after vaccination. Therefore, it is possible that a person infected with a disease just before or just after the vaccination could develop symptoms and get the disease because the vaccine has not had enough time to provide protection. Types of vaccines. Scientists take many approaches to developing vaccines. These approaches are based on information about the infections caused by viruses or bacteria. The vaccine will prevent such as how germs infect cells and how the immune system responds to it. Practical considerations such as regions of the world where the vaccine would be used are also important because the strain of the virus and environmental conditions such as temperature and risk of exposure may be different across the globe, just like we're seeing in coronavirus. The vaccine delivery options available may also differ geographically. Today, there are 5 main types of vaccines that infants and young adults commonly receive in the US. Number one, live attenuated vaccines fight viruses and bacteria. These vaccines contain a version of the living virus or bacteria that has been weakened so it does not cause a serious disease in people with healthy immune systems. Because live attenuated vaccines are the closest thing to the natural infection, they are good teachers for the immune system. Examples of live attenuated vaccines include measles, mumps, and rubella vaccine, and varicella, which is the chickenpox vaccine. Even though they are very effective, not everyone can receive these vaccines. Children with weakened immune systems, for example, who are undergoing chemotherapy, cannot get live vaccines. Inactivated vaccines, number two, also fight viruses and bacteria. These vaccines are made by inactivating or killing the germ during the process of making the vaccine. The inactivated polio vaccine is an example of this type of vaccine. Inactivated vaccines produce immune responses in different ways than live attenuated vaccines. Often multiple doses are necessary to build up and maintain immunity. So not just one dose, but many doses to build that up. Toxoid vaccines prevent diseases caused by bacteria that produce toxins or poisons in the body. In the process of making these vaccines, the toxins are weakened so they cannot cause illness. Weakened toxins are called toxoids. When the immune system receives a vaccine containing a toxoid, it learns how to fight off the natural toxin. The DTaP vaccine contains diphtheria and tetanus toxoids. 4, subunit vaccines include only parts of the virus or bacteria, or subunits instead of the entire germline. Because these vaccines contain only the essential antigens and not all the other molecules that make up the germ, side effects are less common. The pertussis or whooping cough component of DTaP vaccine is an example of a subunit vaccine. So just parts. And then lastly, conjugate vaccines fight a different type of bacteria. These bacteria have antigens with an outer coating of sugar, a sugar-like substance called polysaccharides. This type of coating disguises the antigen, making it hard for a young child's immature immune system to recognize it and respond to it. Conjugate vaccines are effective for these types of bacteria because they connect or conjugate the polysaccharides to antigens that the immune system responds to very well. This linkage helps the immature immune system react to the coating and develop an immune response. An example of this type of vaccine is the Haemophilus influenza type B or HIB vaccine. There are 4 reasons that babies and even teens or adults who receive a vaccine for the first time may need more than one dose. Not just one, more. And not everyone needs more than one. For some vaccines, primarily inactivated vaccines, the first dose does not provide as much immunity as possible. So, more than one dose is needed to build more complete immunity. The vaccine that protects against the bacteria HIB, which causes meningitis, is a good example. For some vaccines, after a while, immunity begins to wear off. At that point, a booster dose is needed to bring immunity levels back up. This booster dose usually occurs several years after the initial series of vaccine doses is given. For example, this is the case of the DTaP vaccine, which protects against diphtheria, tetanus, and pertussis. The initial series of 4 shots that children receive as part of their infant immunizations helps build immunity. But a booster dose is needed at 4 years through 6 years. Another booster dose of these diseases is needed at 11 years or 12 years of age. This booster for older children and teens and adults too is called Tdap. So every time you get a tetanus shot, this is an example where the dose, it's like a booster dose that's needed to bring your immunity back up. For some vaccines, primarily live vaccines, studies have shown that more than one dose is needed for everyone to develop the best immune response. For example, After one dose of MMR, the MMR vaccine, some people may develop enough antibodies to fight off infection. The second dose helps make sure that almost everyone is protected. So some people after the first one might get it, but not everyone. Finally, in the case of flu vaccines, adults and children 6 months and older need a dose every year. Children 6 months through 8 years old who have gotten a flu vaccine in the past or who have never gotten a flu vaccine in the past or have only gotten one dose in the past years need 2 doses the first year they are vaccinated. Then an annual flu vaccine is needed because flu viruses causing disease may be different from season to season. Every year, flu vaccines are made to protect against viruses that research suggests will be most common. Also, the immunity of a child gets from a flu vaccination wears off over time. Getting a flu vaccine every year helps keep a child protected, even if the vaccine viruses don't change from one season to the next. So in the example of the flu, it'll get mutated pretty much every year. And so scientists try to figure out which strain is going to come into the population, which is why we need a flu vaccine every year. The bottom line, some people believe that naturally acquired immunity from having the disease itself, is better than immunity provided by vaccines. These people are called anti-vaxxers. However, natural infection can cause severe complications and be deadly. This is true even for diseases that many people consider mild, like chickenpox. It's impossible to predict who will get a serious infection that may lead to hospitalization. So you should just be safe and get the vaccine. Vaccines, like any medication, can cause side effects. The most common side effects are mild. However, many vaccine-preventable disease symptoms can be serious or even deadly. Although many of these diseases are rare in this country, they do circulate around the world and can be brought into the U.S., putting unvaccinated children at risk. Even with advances in healthcare, the diseases that vaccines prevent can still be serious. And vaccination is the best way to prevent them. So that's the article. I hope this gives you some assurance as we're living in a quarantine world and coronavirus is our reality. Scientists are working hard to try to develop a vaccine that's effective and that's safe and that can be implemented as quick as possible. China's getting close, I think, to developing a vaccine that can work. And I think the issue now is going to be, how do we get it out to everyone in the population? We have millions and billions of people in the world. How are we gonna get it to everyone? So I hope this gives you some assurance, though. Coronavirus, we don't have to just sit and wait for it to come to us. We can take the fight to them by getting vaccinated. And so when the vaccine comes out, I hope you're able to get that. So again, as a reminder, in the description, make sure you click the link for the quiz. There's some reflection questions I want you to answer. And I hope this was a great video that taught you a lot. And if you need more information about coronavirus or anything else, the CDC.gov, www.cdc.gov is a great place to go. And I'll put that link in the description below. Anyways, that's all for now. Peace.